You're a mean one, Miss Grinch. You really are a heel. You're as cuddly as a cactus and as charming as an eel, Miss Grinch. Now, children, on to trigonometry for section 8 about translating the sine, cosine, and tangent functions. I hope that you enjoyed that. You know who you are. Okay, so I'm looking at this particular function, and I see that it has been translated. I see that it has been translated to the left 2 pi over 3 units. Okay, that's the only thing that has happened in this particular sine wave. So, I know that the period has not changed. I know the amplitude has not changed, right? Because no scale change has been done in either the horizontal or the vertical directions. And let's see here. 2 pi over 3. We know that's 120 degrees. So that's 2/3 of a pi. So if this was the old starting point, and there's negative pi over 2, negative 2 pi over 3 has to be right about in here. Okay? Because imagine that you are splitting pi up into 3 equal pieces, right? Okay, maybe I should have done that. So, you know, this one would be 1 pi over 3, and this would be 2 pi over 3. Obviously, pi would be 3 pi over 3. And that would be negative 1 pi over 3 and negative 2 pi over 3, and I just run out of room for more on the scale. So now I want to move all the way to the right 2 pi units. Okay? So that would be this point right here. It happens to be 2 pi over 3 shoved over to the left from where it used to be. And this one had an x-intercept at pi, but it got moved over to the left 2 pi over 3 also. Halfway in between these two, I would have my highest value at 1. Guess I should have put it over there since it's about right where it needs to go. And halfway in between these two, I would be at my lowest value at negative 1. So there's my sine wave. Whoops. Not my best work. I mean, my best work was when I sang that song a little bit ago, but, you know, don't want to rub it in on too much. Would you like another? Ah, no, I can't. Not today. I can't make somebody that mad in the same video. Have to spread it out over a little bit of time. Y equals cosine. Looks like a cosine wave that has been moved to the right, pi over 4. Oops, 4. Said 4. Why did I write 2? I don't know. And it's been moved up 2 units. So this has a vertical and a horizontal component to it. So remember that if you moved it up 2 units, then the center line of the graph has moved up. It is no longer the x-axis. We know that the period of the function is still 2 pi. We have not changed that because no scale changes occurred. We know that the amplitude is still 1 because no scale change on the vertical has happened. But we do need to think about, okay, so here's pi, and here's 2 pi, and we are splitting this up into 4 pieces, right? Each one of these representing a pi over 4, right? Pi over 4. 2 pi over 4, 3 pi over 4, and so on. So this over here would be negative pi. So we moved our cosine wave to the right, pi over 4. So take the old point where the cosine used to start out and move it right pi over 4 and up 2. So it's right here. And then we're going to go 2 pi units to the right, which would take me past 2 pi by pi over 4. Halfway in between, we would be at our lowest point, and halfway in between here and here, and halfway in between here and here, so we could get our wave. Now, I know it looks like I've squished it together, but I didn't really squish it together. I didn't do a scale change of any sort. I just had to make my scale smaller because in the vertical direction, because I needed to move it up 2 units. Now, I really, on these 2 particular graphs, I need to go back and highlight something. Maybe even go back and look at just a basic sine wave. So let me just look at a basic sine function in, on this particular graph with x-intercepts at every pi units. So something basic like this. There's a point called HK. Now, so HK is that's the phase shift, right? Because it has an H in it, and that's the vertical shift because it has a K in it. Phase, vertical. You know all about that. But so phase shift is just your horizontal, it's your left and right movement. They refer to that in the book, so I wanted you to see that term. And vertical shift, obviously, that's our up and down movement. Now, in this particular graph, you see that the vertical shift and the horizontal shift are both zeros, okay? Nothing has been changed about this particular graph in terms of shifting it around. 0, 0, that would be my HK. Okay, it sits on the center line. It sits on the way up the hill. Now you might want to say, well, what do you mean on the way up the hill? Well, imagine, kind of like a roller coaster. Okay? And you're moving from left to right. I mean, this point right here is also on the center line, but it's on the way down the hill. We want to be on the way up the hill. Okay? So, sits on the center line on the way up the hill. In this particular graph, we actually changed that, okay? Because we moved to the left to 2 pi over 3. So our HK moved over to here, all right? And then everything else we could graph from that particular moment. So what happens on a regular cosine wave? Where does HK sit on a regular cosine function? Well, sorry, it looks like it's a little bit above 1. How dare I? Well, here's your basic function here, and we could still see that HK is still 0, 0, and that particular point right there, 0, 0, that's my HK, does not fall on the way up the hill. Does it still sit on the center line? Yes, sits on the center line. But it sits underneath a maximum. Sits on the center line, but it sits underneath a maximum. Now that's an important point because when I go and I look at this particular cosine wave, we first find HK. Now you'll see different teachers put a plus sign. Some teachers do, some teachers don't. They put a plus sign where HK goes, right? And as we start doing more of these translations, it might be a good idea if you start doing that. Now, another thing you might see other teachers do, which is not a bad idea, is to make a box, right? And that box is going to have one of the cycles in it. Now, is that box critical and important? Not necessarily, but it may really go a long way as to helping you understand. So if you're doing a problem like this and you want to say, okay, I know it's going to start here, 2 pi units later, and it goes up to 1, and it goes down to -1. Well, there's your box. And you can and draw one of the graphs or one of the cycles inside that box. Well, what happens with a basic tangent function? Where, in terms of h's and k's, we know that at negative pi over 2 and positive pi over 2, we have these asymptotes to the graph, right? I'm just going to look at one of these cycles. I'm not going to draw a bunch of them. Whoops. Almost crossed my asymptote. Whew! That was close. Anyway, hk, right, still 0, 0 on a basic tangent function. Sits on the center line. Middle of tangent cycle, for lack of a better term. Middle of the tangent cycle. Okay, now here's a picture of a particular graph, and you are asked to identify the function. We obviously know this is a tangent function. So I'm looking at the picture, and I see that the center, hk, has been moved to the left pi over 4 units. So all I have to do is write an equation that says left pi over 4 units. Well, obviously that would be x plus pi over 4. Now we could also write a rule for that, We know how to write translation rules, so I could ask you for a translation rule. The rule never lies, right? So the rule would have said x minus pi over 4, comma y. And why is it just y? Because nothing happened to the y value. Okay, I want to look at example 4 in the book, so I wrote a note to myself just so I could look at that particular example. It's a fairly complicated example. I don't expect you to write all this stuff down, but, for the people at home that are watching without actually listening to the video, maybe they can copy it down just for fun, okay, and then we can have a good laugh at them in class. No, we wouldn't laugh at them. That would be ridiculous. My goodness. But I know who you are. There are people out there that aren't listening to what's going on. The maximum inductance in an alternating current occurs when the current flow lags behind the voltage by pi over 2. Assume that the two waves have the same amplitude and period, and that the voltage is modeled by the equation y equals sine x. In a situation of maximum inductance, find an equation for the current and sketch the two sine waves. Okay? Now, so here are the two sine waves. One being just a plain old sine x, that's your voltage. And then your current lags behind, so that means it's a shift of pi over 2 units to the right. Okay? That would be a sine wave, because it says, because the goal in example 4 was simply to illustrate maximum inductance, any sine wave could have been used. Below are the graphs of y equals cosine x and cosine x minus pi over 2, so that would be a pi over 2 shift to the right, which are also out of phase. Out of phase meaning they're not running together, and it's out of phase by pi over 2. Okay? So the voltage wave leading the current wave. The voltage wave would be the blue one. Okay? It's leading, right? And the current is lagging behind. The current, sorry, you can't see colors. The blue one, right? The blue one is the voltage wave, and the orange one is lagging behind. It's getting to the same places, but it's just not at the same time. What they're trying to get at is this point right here. And we already pretty much know this because we've already studied it. says for all real numbers, cosine x minus pi over 2 equals sine x. Now, you know this better as the complements theorem back in section 4.4, where we said when they are complements, we switch x and y. Well, there's the y value there, there's the x value there. But the important thing they're trying to say in this particular example is that the sine wave and the cosine wave are different from each other by pi over 2 radians or 90 degrees. Sorry for the yawn. It's Friday, and I'm ready to go home. Couple more graphs, and we will be. Alright, now, given the function y equals cosine x, and here's a translation rule telling me, remember the rule never lies, correct? So that says right pi over 2 and down 1. I should be able to transform this equation. We should be able to do some of the same things we talked about before. Remember what we would replace with x? We would replace x minus pi over 2. And what would we replace with y? Y plus 1. And then, of course, we would get y by itself, so it would be y equals cosine x minus pi over 2. This one looks a lot like fireproof form. Now, you probably are wondering how it looks like fireproof form. Now that you know more about translations, fireproof form can really be shown to you, right? Not only, and this is what we're going to get into in section 4.9, is putting all of this stuff together, where we talk about scale changes and translations at the same time. But we're not quite there yet, so we'll be practicing more and more of our just changing things into translations or scale changes, and we'll put it all together in section 4.9. For a basic sine wave, we're going to take this translation function which says left pi and up 3, and we're going to make that equation say that. So sine, and we put in here x plus pi, and we put in here y minus 3. Might I remind you, as you're wondering if you haven't seen other videos that I've done on scale changes and translations, that we're already substituting with the opposite, because the rule really tells me what I would replace this x with in order to get rid of pi and get back to the original x. The rule here is telling me what I would replace y with, y plus 3, to get rid of the minus 3 and get back to just plain y. And then, of course, we always usually we solve for y, so we have sine of x plus pi plus 3. So there's my final equation there. Of course, here's my final equation on this one. So I hope you enjoyed that video, and I'll see you next week sometime.